You see this three-lettered word. It is the backbone and reference point of anything related to data. It stands for structured query language, and it is very important. For better context, SQL is a programming language that is used for generating, manipulating, and retrieving data from a relational database. By the way, some people call it SQL, which for now is not really important. You can call it whatever you want. But the question is, in the world of powerful tools and coding softwares, how does a simple tool as SQL take the center stage and become so important that for any job within the data space you apply for, it is being required? And also, SQL is not a new technology. It has been around since the 1970s and has been a household name whenever it comes to programming languages and relational databases, whereas other database management tools have come and gone. So this makes me wonder, how did we get here? And really, why is SQL so important? Well, to answer this question, we need to go back in time and understand why SQL had to be developed in the first place. It all begins with a database. Now, a database is simply a set of collected information. One typical example of a database is a telephone or a contact book that contains phone numbers, home addresses, and names of people. Now, this is useful to get quick access to people's detail, such as their name and home addresses, but you can already tell its drawbacks. If the entries are really large, it will be difficult and really time consuming to locate a contact. Also, people can decide to change their phone number or even their home addresses, and sorting through the contacts to make these updates or to make these changes is theoretically possible, but not practically. All these drawbacks can also be seen to apply to manual data storage system. Say for example, patient record in a filing cabinet. This is an example of a paper database, and it can be very cumbersome. Based on this, when the first set of computer systems were developed, an electronic database system was developed alongside, which are basically a computerized data storage and retrieval mechanism. Unlike the filing cabinet database that makes use of paper, the computerized database system stores data electronically, hence making a database system capable of retrieving data more quickly, indexing data in multiple ways, and delivering up to minute information to its users community. Now, early database systems stored data in magnetic tapes and data input was made via punch cards. This technology reads data sequentially. That is, if you need to get a specific data located in, say, position 700, you will have to start reading the whole database from 1 until you get to 700. You can already see the drawback of this system. You will be unable to access data points randomly. Also, since computers of that era had very little memory, multiple requests for the same data generally required the data to be read from the tape multiple times, which can be very time consuming. This database system can be seen to be obviously better than the paper database system, but they are not even as good as what came later on or what we have right now. For context, modern database systems can manage terabytes of data spread across many fast access disk drives, holding tens of gigabytes of that data in high-speed memory. Over the first several decades of computerized database systems, data was stored and represented to users in various ways. The first upgrade from the magnetic tapes and punch card based system was as a result of a situation where NASA tried to put a man on the moon via the Saturn V rocket. They needed a database system that can handle the data being collected from the mission. At that time, the current magnetic tapes and punch card system being used was too slow and manual and relatively bad for the project. This prompted NASA to contact IBM to develop a better database system, as IBM was already building parts of the rocket that was going to be launched. IBM developed the Information Management System, IMS for short, and came up with a database system which is known as the hierarchical database system. Now, a hierarchical database system is a type of database that stores data in a tree-like structure where records are organized in parent-child relationships. Each parent node can have multiple child nodes, but each child node has only one parent. This results in a strict one-to-many relationship, similar to a family tree or a file system on a computer. For example, in a company database, a single department, in quotes, parent, may have multiple employees, in this context, children, but each employee belongs to only one department. One of the defining characteristics of the hierarchical database is the use of pointers to navigate through the data. These pointers help establish the connection between records, allowing for fast retrieval of information when the structure is known and well defined. However, the rigid format of hierarchical database means they are not suitable for handling complex many-to-many relationships or unstructured data. Making structural changes to the database often requires significant reworking, which can be time-consuming and error-prone. The limitations of the hierarchical database model ushered in another, which is the network database model. The network database model is a type of database system that represents data in a flexible graph structure where records are connected through multiple relationships. Unlike the hierarchical model, which allows only one-to-many relationship, the network model supports many-to-many relationships, enabling a child record to have multiple parent records. This flexibility makes it more adaptable for complex data relationships, such as in manufacturing or organizational structures where an employee might work in multiple departments. While the network model offered more flexibility than the hierarchical model, it eventually lost popularity due to its complexity and the rise of relational database models in the 1980s. Relational databases, which used tables and SQL for querying, were easier to understand, modify, and scale. Nevertheless, the network model's efficiency in handling large datasets and complex relationships made it suitable for certain legacy systems, some of which are still operational today in industries like defense, telecoms, and banking. One thing I want you to know is that both the hierarchical and the network database system makes up the non-relational database system and are alive and well today, although generally in the mainframe world. Beginning in the 1970s, however, a new way of representing data began to take root, one that was more rigorous yet easy to understand and implement. In 1970, Dr. Edgar F of IBM's research laboratory published a paper titled A Relational Model of Data for Large Shared Data Banks, which proposed that data can be represented as sets of tables and based on set theory and predicate logic. Unlike the hierarchical and network models, which used pointers and fixed structures to link records, the relational model organized data in tables called relations, where each table consists of rows, aka records or tuples, and columns, aka field or attributes. Now, each row in a table is uniquely identified by a primary key, and relationships between tables are established using foreign keys, which refer to primary keys in other tables. One of the key strengths of the relational model lies in its simplicity and flexibility. Data in a relational database is stored independently of how it is used, meaning that changes in the structure or use of data do not require changes to the way the data is being stored. This separation of data from applications is a major advantage over older models. Now, the relational model also supports powerful querying capabilities through structured query language, SQL, a standardized language used to retrieve, insert, update, and delete data. Relational databases are typically managed using Relational Database Management System, RDBMs for short, such as MySQL, PostgreSQL, Oracle Database, Microsoft's SQL Server, and SQLite. These systems provide the tools and interfaces necessary to define data structures, enforce rules, manage transactions, and ensure concurrent access in multi user environment. Features like ACID compliance, by ACID I mean atomicity, consistency, isolation, and durability, ensures that data remains consistent and reliable even in the event of power failures, crashes, or concurrent modifications. Over the decade, the relational model has become a de facto standard for data storage in countless industries, from finance and healthcare to retail and government. Its widespread adoption is largely due to its balance between efficiency, scalability, and ease of use. Although newer models like NoSQL, NewSQL have emerged to handle unstructured data and large-scale web applications, relational database remains dominant for applications requiring structured data, complex querying, and robust transaction management. Along with Codd's definition of the relational model, he proposed a language called DSL/Alpha for manipulating the data in relational tables. Shortly after Codd's paper was released, IBM commissioned a group to build a prototype based on Codd's idea. This group created a simplified version of DSL-Alpha, which they called Square. Refinements to Square led to a language called SQL, which was finally renamed SQL. SQL allows users to interact with data using human-readable commands that resemble plain English, making it relatively accessible even to non-programmers. It is used to perform a wide range of tasks, grouped into several main categories. Now, the data query language, DQL for short, particularly the select statement, is used to retrieve data from one or more tables. The data definition language, DDL for short, includes commands like create, alter, and drop. Is used to define and modify the structure of database objects such as tables and indexes. The data manipulation language, DML for short, with commands such as insert, update, and delete, allow users to change the data within existing structures. And finally, data control language, DCL for short, commands like grant and revoke manage user permission and access control. One of SQL's most powerful features is its ability to perform complex queries involving multiple tables thanks to the join operations. These joins, such as inner join, left join, and full join, allow SQL to retrieve related data with different tables based on shared keys. SQL also supports filtering, that is the where clause, sorting, order by, grouping, group by, aggregation functions, that is the sum, the average, the count, and so much more, and subqueries, which allows nested queries inside other queries. These capabilities make SQL a highly accessible and versatile tool for data analysis and reporting. SQL also plays a critical role in ensuring data integrity and consistency through the use of constraints such as primary key, foreign key, unique, check, and not null. SQL also ensures that data adheres to rules defined by the schema, thus reducing errors and maintaining relational integrity. Additionally, SQL databases are ACID compliant, meaning they support atomicity, consistency, isolation, and durability. These are 4 key principles that guarantees reliable processing of transactions even in concurrent or crash-prone environments. In today's data-driven world, SQL remains an essential skill for data analysts, data engineers, software developers, and anyone working with structured data. Despite the rise of NoSQL databases, SQL has adapted and remained relevant. Many NoSQL systems now offer SQL-like query capabilities due to its clarity and expressiveness. Moreover, its integration with tools like Power BI, Tableau, Excel, and Python, via the usage of libraries like SQLite 3 or SQL Alchemy, makes it a critical component in both business intelligence and data science workflow. Let me quickly run you through how SQL is important to a lot of fields. SQL is foundational in data analysis and data science because it allows professionals to extract, filter, and summarize large volumes of data directly from databases. Analysts use SQL to clean data sets, calculate metrics, and can join multiple tables to create a coherent view of information. Data scientists often begin their workflow with SQL when accessing structured datasets before moving into Python, R, or other machine learning tools. Since most company data is stored in relational databases, SQL is the gateway to insight, forming the first step in exploratory data analysis and model building. For backend developers, SQL is critical for building applications that interact with databases, whether it's a web app, a mobile app, or an enterprise system. Developers use SQL to perform crude operations, that is, create, read, update, and delete. In BI and reporting, BI professionals use SQL to query databases and produce reports that help businesses monitor performance, identify trends, and make data-informed decisions. Tools like Tableau, Power BI, Looker rely on SQL or SQL-like languages to connect to data sources and retrieve relevant information. For database administrator, SQL is the primary language for maintaining and managing relational database systems. SQL importance cuts across virtually every tech role, including machine learning engineering and cybersecurity, as far as these roles interact with data. SQL is very important. Its versatility, efficiency, and wide adoption make it a non-negotiable skill in today's ecosystem. If you enjoyed this, please do not forget to like and share the video. If you are a data analyst and you have been thinking of transitioning into machine learning engineering, you can check out this video. We'll see you in the next one, and bye for now.